All right, welcome back. We are Game 3001 in the winter 2020 semester at George Brown. It's week 9, part 2 of our broadcast. We're going to talk about recursion a little bit. So what is recursion? Anyone know what recursion is? One thing to know is that the concept of recursion is used extensively throughout artificial intelligence, all kinds of places, right? So whenever we use recursion, we have a function a lot of times that calls itself. A function that calls itself. A lot of times we use this because it makes logical sense in our head. It's easier for us to conceptualize of something that we want to use again from the function that we're calling. So an example of that would be like, okay, I want to find a path. But I want to find the shortest path. And I get to a tile, and the tile has multiple ways of going. I have 4 neighbor tiles. I want to explore each of those neighbor tiles. Each viable neighbor, I want to explore from that particular position, right? I want to go that direction. I want to use the same algorithm. So each tile I want to go to, right? So I go to the first tile, and I go, okay, cool. I have 4 neighbors, or 3 neighbors, right? From the first tile. And again, we can pull up a map like this. Let's suppose I pull up a little map, right? And I mark some of these tiles as let's say mines, right? And let's just mark these as what they are. Let's give some values to these things. These are closed, so it starts off, and here's my start tile. And my first one, I come to this point, let's suppose, and I mark these ones off as closed. I come to this point. Let's suppose I have to go this way. I mark these ones as this one is closed, and then I go here. This one's already marked as closed. I don't want to mark this one or these two because they're so on. So I'm going to keep going through this until I get to where I'm supposed to go, the goal. But here where I marked this as open because this was the closest tile, and I marked this one as closed, I could have also gone this way, even though it's not the closest one, but I could have. And I could have also gone this way or this way. And we should explore those opportunities, paths, using the same heuristic to get to this. So let's suppose I did that, and I'm just going to clear up all these reds and greens. Okay, so so these reds are, I'll make them white. So let's suppose, and I'm showing you this because it's in slow-mo. I want to get through this corridor, right? And let's see what these values would be. If I'm using the Manhattan distance from this, what would be the Manhattan distance for this tile? How do I calculate it? You guys remember? I add in all the tiles to get to it. So I go 1, 2, 3, 4, 5, 6 on the x-axis plus 1, 2, 3, 4, 5. That's 11, right? Plus 1, 2 from the distance from here. So this would be like 12. Okay? And what about this one? So again, I would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Plus 1 from the distance, this is 13. What about for this one, right? And I think maybe I calculated wrong. It's probably like 12. Sorry, this would be 12, 12. These are all in line. See this line here? This would be like 11. Okay, so I'm just using the same numbers here. Okay, so you can see it. So there's all my numbers, right? You can see that these are 9s, these are 8s, and you can see the pattern. Okay, make sense? And then this would be 13. So 13, and this would be like 14. Okay. All right, so knowing that I've got these numbers, then again, I could choose one of these two 12s, right? And if I chose this one, I would call find shortest path on this one. So then from here, I would call find shortest path on this one. Okay, so where am I going from here? Find shortest path. Well, I'm going here to the 11. Okay, from here, I'm going to call find shortest path from this one. Well, I go here to the 10. Okay, it's a dead end. So I return back to this one. I call now find shortest path on this one. So I go here. Find shortest path on this one. I go to the 11. Find shortest path on this one. So I go to the 10. Find shortest path on this one. I go to the 9. Find shortest path on this one. I go to the 8. Find shortest path on this one. I go to the 7. Go back to this one. Find shortest path on this one, right? I go to the 8. Find shortest path on this one. You see how what's happening, right? I wouldn't stop. I would keep going. Okay, cool. Find shortest path on this one, 7. And then I would go 6, 5, 4, 3, 2, 1, and goal, right? So that's one of the paths. But the way I found that is I marked these ones, the ones I failed, this one and the other one, this one here, I think, or wherever the other one was. I think it was another path up here, right? I've marked this one and this one as closed, failure, right? But I've got a path. Okay, cool. That's the first one. Then I do it again for A star. So I go, cool, let's try this way instead, right? So come here, from here I go up here, from here I go up here. Same problem. I go this way and I found the same ways, both ways, but I count the number of tiles. So if I was going to find this way, it would be this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 would be the path length. Here, 1, right? And again, I would count until I found the shortest path length from this one. So this one would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 is shorter than 17. So 15 is the shortest path so far, right? And that's just using these two. What about if I went here? Well, here, again, I would go this way. You can see that I would only try and follow the tiles, right? So I'd go here. There'd be an extra length. It'd be the same as this one, right, in terms of length. So I'd go this way. How about here? It'd be longer, and that's the only, those are the ones I would try. So my path length for this case would be like 13, or whatever it is, right? But that's what you want A star to do. You want to remark on all the paths that are possible, right? We're not doing that. We're just looking at the first shortest path. And sometimes we'll get into the problem where you'll find dead ends. You'll find a dead end up here, and you'll find a dead end up here because it's closer to this thing. Okay, and this is using Manhattan distance. In this example, we're not using Euclidean distance at all. Okay, so that's what we want to do. That's what we want to do. So what is recursion? How do I do this? Well, a lot of times we can solve the same problems we solve with recursion with just for loops or while loops and multiple function calls. Okay, but let's suppose there's a classic problem in programming. We want to find the next Fibonacci number in the Fibonacci sequence. That's a classic problem. Okay. Does anyone know what the Fibonacci sequence is? It occurs naturally, or it occurs in nature, and it goes like this: 0, 1, 1, 2, 3, 5, 8, 13, and so on. What happens is, to find the next number in the series, you add the previous number to it. And the two numbers that start off are 0 and 1. Okay, so 0, 1, those are the two numbers. To find the next one, you take 0 and you add it to 1. And now the next number is 1. So 0, 1, 1. Okay, I want to find the next number. So you take 1 and 1 and you get 2. You want to find the next number. You want to get 2 and 1 and you get 3, and so on. You keep doing that. Or what about if I want to find the 50th one? The 50th number, the 50th term, right? Well, you can do it with some kind of loop, right? And let's just look at that loop. We can probably use a loop, right? This is one way of doing it. We can use a loop that goes like this, right? We can say that, okay, I want to start off with T1 and T2. T1 is 0, T2 is 1. The next term is 0. And what I want to do is I want to loop through. The next term is T1 plus T2. While the next term is less than or equal to n, whatever the number of terms I want to find. Let's suppose my number of terms is 10. While the next term is less than or equal to 10, then I want to say that T1 is equal to T2, T2 is equal to the next term, and blah, 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 and we'll find the terms that way, and you can see the output that you're going to get. Okay? 0, 1, 1, 2, 3, 5, 8, and so on. So that's one way of doing it. You can also do it a longer way, where you have a for loop to do the same thing, right? Or you can use recursion. And the recursion version is this. Okay, so the way it works is this. I would say, okay, take the number, let's say 10. If x is equal to 1, it's not. Or x is equal to 0, it's not. Then return x. Otherwise, we want to return a number that I'm going to call itself. So I'm going to say, okay, so 10, so say the number is 10. So 10 minus 1 is 9. Okay, 9 comes into the new call. And the way recursion works is, as an example, I get a, I take the actual function and I make a copy of it and I put the copy on the stack. The whole function, right? I push it onto the stack. And then I run with that function on the stack. And when I'm done with that function, I pop it off the stack and I go back to the calling function again. That's what happens. But I do it like a domino effect. I do it a bunch of times. So let's follow this now. If the number was 10, right? So it'd be 10 minus 1, so it's 9. So 9 would come in. I create a new function. So this is my first call. I pop a new function onto the stack. All right? 9. Is 9 1 or 0? No. 8, 7, 6, 5, 4, 3, 2. Keep counting, right? And then when I get to 2, 2 minus 1 is 1. Okay, this is the base case right here. This is the base case, right? So x is 1, then I return x, which is 1. So this becomes, when x is 2, then fib x minus 1 is equal to 1. So 1, okay, cool, plus x, which would be 2 at this point, minus 2, that would be 0. 0, I come here as 0, I return 0. So if it's 1 or 0, it's 0, I return 0, so this would be 1 and 0. So what this means is for the second term, the number is 1. That's what this means. Cool, so I come out of this and I go to 3. 3 minus 1 is 2, right? That's what happens. But we know that 2 returns already 1, right? So it's 1, right, plus 3 minus 2. It comes to this one now, 3 minus 2. So it goes 3 minus 2 is 1. So 2 plus 1 is 3. And then it keeps counting, and it keeps adding, and it creates the same effect. 1, 1, 2, 3, 5, 8, 13, and so on. Okay? So I can do the same thing with recursion. However, warning, recursion, the problem with recursion, guys, is it's difficult to troubleshoot. And sometimes your mind gets a little bit squirrely with it. You're like, wait, what? How do I go to the next one? Well, what happens here is I'm adding, for this one line, I'm adding 2 copies of the same function onto the stack. And what happens is if you don't have a good base case, so let's say, for example, your base case is not a good base case, you can keep popping stuff onto the stack over and over and over again, like I showed you earlier, and we'll have something called a stack overflow, right? Where you've run out of stack memory altogether. And you never want that to happen for your application, ever. That'd be the worst case scenario, right? Just like an endless loop, but worse. It's an endless loop that'll crash your system because you'll run out of memory on the stack. Okay? So, yeah, that's not cool. So this is what we want to do. So here's the challenge. Challenge for you guys. So you guys get a few minutes. I want you guys to write a recursive function, we'll call it recurse, that counts from 0 to 10. It counts from 0 to 10. Can you do it? Write a recursive function, we'll call it recurse, that counts from 0 to 10. You could write it in a for loop. The for loop would be like this. For I is equal to 0. Right, int I is equal to 0. Where I is less than 10, I plus plus. And then count I. Keep doing it. See out, just output I, whatever the value is. That's a for loop. It would take 2 seconds to do that, right? But what if you want to do it in a function? What if you want to use a recursion for this? How would you do that? How would you set up a recursive function? Any idea, guys? Can you do it? Shouldn't take you more than a few minutes. For the people watching the video, just fast forward to the answer, right? But here, for you guys, I want you to take a few minutes and do it. Can you write a function called recurse that counts from 0 to 10? You should already be done, pretty much. Doesn't take much. Tower of Hanoi, that's the other one. Look, it even tells you C++ program for Dijkstra's shortest path. Related questions, right? Because we use that. We use that for that. And I'm sure, I'm curious. Let's take a look at that while you guys are doing your thing. Here's your input and your output. And does it show a C++ algorithm? Yeah, probably does. Does it count? Does it call itself? Dijkstra. Or is it using for loops? Min distance. I'm just waiting for you guys to do the recursive little algorithm. Yeah, this just uses for loops. There's no recursion here at all. For loops and while loops. That's neat. Okay, so by now you should be done. Let's do it. So I said I want you guys to create a little algorithm. Let's do it in the play scene, okay, or in the start scene actually. Right. So we'll do in the start scene. We'll go to Solution Explorer, and we'll go to the start scene. Start scene.h. Let's make a new function. Okay, we'll call it recurse. It'll return an integer, m_recurse, and we'll pass in an integer. Call it the number. Right? There's recurse. Okay, so again, we're in start scene.cpp. We're going to the other scene. All right, cool. So it does all this, and what I want to do with the recursive function is this. It's going to say that whatever the number is, let's output it. So std cout. I want to say here's the number. Right? Num. Okay, so it outputs the number, whatever the number you pass it. And then it says this. It says if the number that you have, first of all, let's do a num plus what? Plus. So we'll increment the number. If the number, right, is equal to, and we're going to say 10, because we said 10, right? Then return the number. Right? If the number is equal to 10, return it. Right? Return 10. Otherwise, don't return 10. I want to return m_recurse. And we'll pass in the number. There's other ways you can write this, and I'll write it the other way first. So this is the one way to write it, and if I was to write this, let's call it here in the start functions. We'll say that, hey, m_recurse. Let's pass in a 0. And again, all I've done is I've made the function, and here in the start function, I'm just calling it. Okay. And let's print the final number out. So we'll say that auto final num is equal to this thing, right? Whatever we're going to get. And let's do a std out. Let's just do we'll output the number. So say final number is equal to this, right? Okay. What do you think the final number will be? Will this do what it's supposed to do? Will it count from 0 to 10? Well, let's take a look. So let's trace it before we run it. Okay, so we get 0. 0 comes in. We print out the number 0. Num plus plus will go to 1. Is 1 less than 10 or equal to 10? No, it's not. So we go here and we return recurse. Okay, but wait a minute. We go to return. So now it goes to 9. Sorry, it goes to 1 goes in here. So now it goes to 2. Now it goes to 3. Now it goes to 4. I'm speeding up. It goes to 5. 6, 7, 8, 9, 10. Okay, it goes to 10. Num is equal to 10. Cool. If it is, return the number, 10. Okay, 10, it returns 10. It returns 10. It returns 10. It returns 10. Because it returns the number, whatever the number is. Right? And then, it finally, at the end, it returns 10. I don't know if you see that. Because the number has been changed. Right? Okay, so then we should get 10 at the end. We should. Isn't that what should happen? 9. Why 9? Let's see. Let's see what we get. 9 or 10. And this is where we get like funky squirrely with recursion, because we don't have an idea of what happens. It's a silly exercise, truly, to count to 10. But just starting to count to 10 is kind of interesting. Okay, so there we are. So 10. Yay, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what we want to return, right? What if we redid this differently? So instead of doing it like this, what if we did something else? We said that, how about if my num is less than 10, right? If my num is less than 10, then I want to say that recurse, m_recurse, and I want to pass in the number, and then I want to return the number down here, okay? There's a bug with this one. So what would be the number that I return now? And would it count to 10? I think, again, there's different ways of writing this. By the way, this part right here, this is the base case, right? So base case, kind of, right? So what is it? What would it return? Guys, this is a very silly example, but you're going to run into places like online for AI where you call, the value itself, and it's going to be like many, many values, and you're going to go like, okay, I want to break my brain now. I'm not happy with this. How does it work? 9? No.
10.
No. What is the value? Come on, guys. How about the guys over here? What is the value? It's not 9, it's not 10. What is the value that I'm returning? In this case, there's a bug, I told you. How about my friend in the back? What's the number that I'm going to get? You have no idea. None at all. It could be from 0 to 10. Which one? Why don't you... Huh? Infinity is not the number. No. I like your thinking, though. What? Someone said 0. No, can't be 0. Okay, let's trace it together. Here, let's trace it. So it goes like this. It goes through, it starts at 0. It increments to 1. So it can't be less than 1. Okay? Because it increments it to 1. And then it goes through here. Okay? And is 1 less than 10? Yes, it is less than 10. Recurse. It goes through here, and it goes here. This 1 goes to 2, goes to 3, 4, 5, 6, 7, 8, 9. When 9 is less than 10 is okay. But when 10 is less than 10, it's not. And so what happens is it skips this whole thing and returns 10. Okay, it returns 10 from this one, but guess what happens to the 10? It gets lost because I'm not passing it anywhere, right? I can call a function. This is the bug right here. So what's happening is it doesn't matter what it returns. It comes back to the first case. The first time it popped it up on the stack, and number was 1, so it returned a 1. That's the answer. And you wouldn't have seen that because you're like, wait, but it should be returning something. But there is nothing that sure, it returns, right? This thing does return a value, but you're not capturing it in any way, so it's gone. That's the bug, right? So if I run this thing now, the answer should be 1. The final number is 1. Let me show you. See? Because you're not doing anything with the number. Now, if I wanted to fix this, I can just put num is equal to, right? And then we're good to go, right? Does that make sense? Because now I'm capturing the number every single time. So now it's going to return 10. So if you run this now, you can see that we're going to return 10, right? And this silly mistake, this bug, is one of the things that can plague you, right, when it comes to running recursion functions. Recursive functions are not recommended generally when you come to code. The general consensus when it comes to recursion is avoid. Why? Difficult to troubleshoot and maintain. Very difficult to understand the base case. Very challenging. So we try not to use it. We try and make use of while loops and for loops in their place. However, as you saw with Dijkstra's algorithm, it can be really complex, the for loops and the while loops and everything else that comes into play, right? And let me take a look at that for a second. If I go back and look at Dijkstra, okay, so Dijkstra's algorithm, the one they show here online, I mean, it's from here all the way down to here, okay? Let's see if we can find Dijkstra recursive. So Dijkstra C++ recursive, right? So I want to find recursive algorithm for Dijkstra, and let's see. Here's the minimum distance, right? So we have a minimum distance function, and we have print the path, and then where's Dijkstra? Here's Dijkstra, right? We have a graph, whatever it is. And is it using recursion or not, or just using minimum distance? Yeah, no. And there's the graph. There's the graph of the distance, right? Because it shows you the vertex and the distance between each one. But this is not using recursion again. This is using for loops, right? That's what this is using, for loops, because the minimum distance is not recursive either. So it's not really the way to go. Okay, let's see if we can find recursive and iterative. No, I'm not going to go there, that's for sure. I just want to see a version of that on GitHub. Sure. Let's see if there's one on GitHub that we can see that's recursive. So Dijkstra, and this is not what we're looking for, different arcs. And the graph, it's neat, but that's not what we're looking for. Nope. Yeah, but anyways, it's there, and you can find it. What I was trying to show you guys was that that you can find a recursive algorithm that'll be much smaller to write, right? However, more difficult to troubleshoot. More difficult to troubleshoot. And I just want to see where I can find this thing. So here's contains node, right? And this is the depth first algorithm. And I'm wondering if it'll call itself depth first again. But anyways, it's very interesting the way you can use the contains node. Here it is. There it is right there. So depth first is calling depth first, right? It's an example of that. So here's your depth first algorithm, and then down here you're depth firsting again, right? So you're calling it from within. Okay, it's not exactly Dijkstra or A star, but you get the idea. Now, this still is pretty darn long, right? So who knows what it would be like if you're just using pure for loops. And sometimes it's just easier from a conceptual in your head, kind of thing to kind of do recursive algorithms. Okay, challenge 2, and this is the last challenge we'll have for today, all right? Challenge 2. I want you to change this function. So it takes 3 values now, okay? It takes the initial number, some kind of iterator, which allows me to iterate instead of incrementing by whatever value I want. So instead of incrementing by 1, I want to increment by 2, 3, 5, however many. So I can count by 2s, like every 2, 4, 6, 8, that kind of stuff. And then for a number of iterations, so 3 values: the initial number, right? The increment, and the iterations. Those 3 things. Okay. And I want to do this. I want to count from 0, and I want to have 10 iterations with an increment of 2. Okay. And the number that I should get back is something like 20. Okay? 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, right? Okay? Can you do it? Can you rewrite this function so I can have those 3 values and write it recursively so I can get back whatever value I want now? And let's write it together because we're running out of time. So the way it works is like this. So again, I go back to the start scene.h. I'm going to have 3 values. The initial number, call it initial num. Sure. And we'll have the second value, which is the increment. And we'll have the last one, which is your iterations. Okay, so that's the new signature. So I'm going to grab those values. And I want to define my function this way. Let's just replace num with initial number for now. I'm not going to use all this, as you'll see in a second. And here it'll start at 0, my increment will be 2, and I want 10 iterations. Okay, pretty simple. All right, so how does this work? So let's define the base case. So I take the number, I print the initial number out. What's the base case look like for this one? So again, I want to have an increment of 2. So this is wrong. This would be plus equals to increment, right? So I'm always going to increment whatever the increment is. So if my number was 0, it's going to go to 2, 4, 6, 8, okay? So what's the base case? Well, I can test to see if the number is if my iterations, I want to check for the iterations. When my iterations is 0, there's no more iterations left, right? Then I'm done, return, right? So that's my base case. If iterations is equal to 0, then I want to return the initial number, whatever that number is. Okay? Otherwise, I want to return m underscore recurse, and I want to take the initial number, which is what I have. Now I'm going to pass in the initial number now, whatever that number was. Increment's going to stay the same, and my iterations minus 1. Will this do what it's supposed to do? What do you think?
We can do it like iterations into initial number instead of that.
Yes. I can divide by it. Sure, I can do all kinds of stuff, yeah?
Iterations into initial number. It will come out with the same value.
Yeah. But let's see how this works. Let's say if I go iterations, so I come in, I go 0 to 10, right? So again, start off at 0. My initial number is 0. I increment it by 2. Is iteration 0? No. Recurse. So now it goes here. So the initial number is now 2. Increment is still 2. Iterations minus 1 is 9. 9, 4, 6, 8, 10, and so on. I keep counting. And then finally I get to a number, and the final number is going to be
20.
Is it? Let's see. I like to see it. I like to think it's 20, but
No, it's not. No.
it's not 20, right? It's nice. It would be nice if it was 20, but it's not 20, right? It's actually 22, right? And it's wrong, right? 22 is wrong because we're getting to the point where it's 22. 22. Why? Because when iterations gets to 0, we've already iterated 10 times. That's why. Right? So that we've actually gone beyond what we want. So it's not 0, it's 1. That'd be the right thing. And then you wouldn't know this because but it'd be like this all the time. Because the way it is your first iteration is already happened. You already had your first iteration. That was the first one. So you don't count that. So it's iterations. So it's 10, 0 plus 1. So you already have 1. So when you have 1 left, that's all you want. You just skip and do that. Now if you do this again, you're good to go. And but Where people go crazy is when we add two recursive functions together. Like for example, what if I did something crazy like this, guys? I said, I want to attach another recurse. I want to do this twice. And I want to get a number here, m underscore recurse, right? So how does this work? Well, what's happening is I'm going to push two versions of my function onto the stack. So two of them, right? So here's the first one. It goes 9, and then here's the second one, also 9, right? So now I should have double, yeah? Okay, let's see what happens. First of all, will this stop? Yes? Well, think about this, right? I'm adding two numbers together, right? Am I ever going to get one? I'm going to reduce, because I'm subtracting, right? I'm subtracting 1, so 9 goes in here, and then 9, it resolves. If I keep doing this over and over again, the result of 9 is like 20, right? 20. And then plus, I'm going to go to like 9 minus 1, and it's going to keep on adding things together. This is going to be a massive number, huge number, right? It's going to come back to me, or a much bigger number. And it might not stop. Let's see if it even stops. Let's see. Does it stop? Okay. Here we go. 10,240, right? How did it go from 20 to 10,240, right? Well, because for every iteration, right, it's going to call itself again. And for every time it calls itself, it's going to call itself 2 times. Every time it calls itself, it's going to call itself twice. And this is an example of what the tree would look like, right? Because every time it calls itself twice. It's kind of, actually it's to the power of 2, right? In some ways. Okay, for that many iterations. And that's why it's crazy the way it is. And you can see the numbers are coming back are weird, right? They're like, they start off, and we've got like 10,000 numbers here, right? So you can start off and you're like, okay, so it's 2, 4, 6, 8, 10, 12. And then once it goes to 18, it's like, wait. It would have gone to 20, but now it goes back to 18, 14, 16, 18, 18, 16, 18. These are all weird numbers we're getting back. Why? Because we're adding the two things together over and over again. We keep on adding those two things together every iteration. It's going to happen twice, right? So every time we're going to go to recurse, it's going to call itself twice, not once, twice, every time, including the second time. So what I mean is, and this is where people get lost, right? They go here. So it goes here, and whenever I call this one, the first one, well, guess what? When it comes back the second time, it calls itself twice. It calls itself twice from the first time. Then it calls itself twice again, and twice again, and twice again, and twice again, until iterations is equal to 0 for the first round, for the first half, this first half. Then it goes to the second half, and it calls itself twice again, over and over and over and over again. Okay? And by the way, guys, this was with 10 iterations. Right? With a number like 3. Let's make it 5. So number 5. And let's make it something insane. Let's see if we can we can kill this thing. Let's make it 100 iterations. All right? And let's see, does it stack overflow on us? With 100 iterations. Right? It's working. It's still working. And like, this is running as fast as it can, guys. Now, I want you to think about this. Do we have a potential to get Stack Overflow? Because what's happened is for every iteration, it adds 2 more, right? It adds 2 more calls to the stack, right? Notice that the numbers are stable around 495. Once it gets to about 495, that was the first case, right? But it makes sense. 5 times 100, 500. Right? So once it gets to about 500, then there's very little variation, but it's going to take 500, and it's going to take that number 500 and split it twice, right? So 500 to the power of 2. What's 500 to the power of 2?
500.
Huh?
2500.
500 times 500, right? 2,500 iterations. Now take that 2,500 iterations and multiply that to the power of 2. 2,500 to the power of 2.
6.
Some crazy amount of iterations, a big number, a really big number, right? And that's what we're talking about. We're talking about like a crazy amount of numbers, and that's not even accurate. But you can see that this is continuous to go, and this will keep going until it's done, right? So you can see that sometimes even simple things like this can make us run what looks like forever. Looks like. It's going to end eventually, but maybe not in anytime soon. Okay? And by the way, if you want to check, let's check. I can always pause, right? And come down to the number and see what the number is right now. Right? So the number is 495, right? My iterations, I can kind of look and see what we're at. I can look at the stack as well. So here's the call stack, right? Here are the call stack. You can see all these versions of my, on the call stack, you have all these iterations. But it's not stopping. It's not stopping. Here's one way we can make it stop. If I say it's less than or equal to 1. If it's less than or equal to 1, because sometimes it'll be skipped, right? That might be okay. If my iterations is less than or equal to 1, okay? Let's try this again. So again, it went, and it's going to keep going for a while. And you can see that it went to the top number very, very quickly. It found that number. What's happening is it keeps splitting and splitting and splitting until it's still a very, very big number. Very, very big number. Okay, so you can see that you can easily like get to the point where this thing isn't going to work, right? How about if I just left it like this, less than or equal to 1? Am I going to get the right number, right? Should I get 500 at the end? Right? No problem, right? It did 500 for us. It did 500. Okay, guys, that's it. We've kind of ran over time. So next week, just a reminder, admin details. So your assignment 2, again, as a reminder, is due Sunday at midnight. Okay, so you've got an extension till Sunday on this one. Next week we'll start, decision trees with code, behavior trees, and state machines. So expect a new template next week to be delivered to you guys for your lab. Okay, guys? Otherwise, enjoy your weekend. Hopefully you'll be able to get that stuff done. I will be available via Discord and email for answering some questions if you need any questions. Okay, guys? Good luck. Thank you.